This video lecture is on limiting reactants. We spent a lot of time talking about stoichiometry, how the mole allows us to relate what is in the microscopic world of atoms and molecules and formula units to what is in the macroscopic world with grams, how we can count by mass. We said the mole was like a dozen and how it used Avogadro's number to help us determine the number of particles in a sample by using masses. And we can do that off the periodic table with molar mass. We can use molar mass to identify formulas like empirical and molecular formulas. And we can use the mole also to actually look at how atoms and elements combine in chemical reactions. When we think about limiting reactants, a limiting reactant is the smallest amount in the stoichiometric ratios. So the actual ratios are really important. So when you think about water and how it combines together, and we look at the stoichiometric ratio, water itself, when it combines, hydrogen gas reacts with oxygen gas to form water. Now, when we balance that equation, we can look at this a couple of different ways. There's a 2 that goes in front of the H2, and there's a 2 in front of the water. You could read this two different ways. You could say 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 2 molecules of water. Well, since we know that the mole allows us to relate the microscopic world of molecules to grams, we can also use the mole to describe this. This perfect ratio to use everything up in our ingredient set would be 2 moles of H2 for every 1 mole of O2. That would be the perfect ratio to get 2 moles of water molecules. And if it's in that perfect ratio, we would have nothing used up. Well, that's typically not the case whenever we're dealing with chemistry. This example here shows that. Notice that I don't have a 2-to-1 ratio of hydrogen to oxygen. I have 10 hydrogens, but I have 7 oxygens. I'm going to run out of hydrogen before I run out of oxygen. So if you look here on the diagram, I make 10 water molecules because it's a 2-to-2 or 1-to-1 ratio from the stoichiometry I just showed you. But I have more than enough oxygen molecules. I have 2 left over. So the limiting reactant in this case would be the hydrogen gas because it's completely used up. I run out of it first, and there's excess of oxygen. Most chemical reactants have a limiting reactant. Most have some reactant that is in excess. So if you think about an excess reagent, you have more than enough of the stoichiometric ratio to form it. And in this case, you've got those leftover oxygen molecules formed. And those are represented in the red molecules on the right-hand side. So when we do a chemical reaction, a theoretical yield is the max that we can get. This is from the laboratory. So if we look at the perfect mathematical operation and we have no loss anywhere, the perfect amount is the theoretical yield. One way to help you remember that is that we're dealing here with the math. Theoretical yield comes from the math. You do the stoichiometry. This is the theoretical yield, finding the limiting reactant. The actual yield, this is what you actually get in the lab. You do the experiment, which has errors in it. We can lose products, places to the surroundings. We may have issues of human error, may have systematic error. That's the actual yield. So it's kind of like percent error in a way, to where when we try to calculate this, percent yield is we take the actual yield, which again, this is the lab yield. This is the lab yield, and this is from the math. Comparing that ratio, multiplying by 100, tells us how efficient we were in the lab. If we were supposed to get a certain number of grams, comparing that to what we got actually in the lab shows us percent yield. It's kind of like a way of doing percent error where you're looking at the accepted value versus what you measured. Same type of idea. So let's talk about stoichiometry and talk about how this works. So let's take a reaction of the formation of ammonia. So that is N2 plus H2 yields NH3. Balancing that equation, we've got to have a 2 in front of the NH3 and a 3 in front of the H2. First step when you're doing a limited reactant problem or stoichiometry of any sort is get the balanced equation. Step 2, let's look at our amounts that we have. Let's say that we have from this (28 grams of N2) and we've got 46 grams of H2. Well, we need to figure out which one of these is going to be my limiting reactant. And the way that I do that is I need to figure out, do they appear in the perfect ratios in the equation? Remember that the equation doesn't show us a ratio of grams, but a ratio of moles. So we're going to do a molar mass. So grams of N2 go on the bottom, moles of N2 go on the top. The molar mass of N2 gas is approximately 28 grams. That cancels out. I've got 1 mole of N2. Multiply together. Let's do hydrogen. Grams of H2, moles of H2. 1 mole is approximately 1 gram. 46 divided by 1, I've got 46 moles of H2. Now in this example, it's pretty easy to tell what our limiter is going to be. It's going to be the nitrogen. The perfect ratio should be 3 moles of H2 for every 1 mole of N2, 3 to 1. Now in my equation, if I have that ratio, I can figure out the limiting reactant. I've got 46 moles of H2, and I only have 1 mole of N2. So the limiting reactant that's going to run out first is going to be nitrogen. Because I have more than enough hydrogen gas. I've got way more moles of hydrogen gas than I need. 43 moles of hydrogen gas left over for excess here in this case. So again, you do and find out the moles and see how it compares to the ratio. And then you can do your stoichiometry from there. Let's do one that's a little more challenging. Let's say that we've got the formation of salt. Sodium plus chlorine, it's a Brinkelhoff, yields sodium chloride, 2 in front, 2 in front. So let's think about these quantities. Get the balanced equation first. So let's say that we have, in this case, 71 grams of Cl2. And let's say that we've got 80 grams of Na. And we wanted to find the limiting reactant. First step is you can't compare the grams and assume that Cl2 is the limiter. Do the math. Molar mass of Cl2 is approximately 71. 35 would be 70, excuse me. Around that. So we've got approximately 1 mole. You go to sodium off the periodic table. Moles of sodium, that's molar mass is about 23. Now, you don't have to complete the rest of the math. Am I going to have more than 2 moles of sodium? Well, if I had a mole of sodium, it would take 23 grams. 2 moles is 46. Well, I've got way more than 2 moles. You don't have to do the rest of the math. That is in excess. So the limiting reactant is chlorine. I can take the moles of chlorine gas and convert to NaCl, and I can know what my limiter is. You need to convert it to moles and compare it to the ratio in the stoichiometric calculations. If you do that, then you do the rest of the mole problems as is. We're going to work several of these throughout the next few days. Make sure and take a look at the practice examples and see how they work out, and we'll talk about them in class. Thanks.